Section: Introduction. In this section, we introduce text embeddings, which are vector representations that capture the meaning and context of natural language. These embeddings are essential for various natural language processing tasks, including information retrieval, text classification, item recommendation, and question answering. We note that pre-trained models, particularly those using bidirectional encoder and encoder-decoder architectures, have been effective in generating high-quality text embeddings due to their extensive pre-training. Recently, there has been a shift towards using decoder-only architectures in large language models, LLMs, for embedding tasks. These models have shown significant improvements in accuracy and generalization, especially when trained with supervised learning. However, they still face challenges in following new task instructions and handling complex retrieval tasks, primarily due to the limited range of instructions they encounter during training compared to the variety of real-world tasks. We highlight the importance of in-context learning, ICL, which allows LLMs to incorporate specific examples into input prompts, enabling them to adapt to new tasks without additional training. Recognizing this capability, we propose a method to create more adaptable text embeddings by including task-specific examples in the query prompts. This approach aims to enhance the relevance and generalizability of the embeddings. While LLMs are mainly used for text generation, we explore how to adapt them for embedding tasks through various fine-tuning strategies. Our experiments reveal that complex modifications to the models do not yield significant improvements. Instead, using the original architecture with the ICL strategy leads to the best results. Our model, named bge-en-icl, achieves state-of-the-art performance on the MTEB and AIR-Bench benchmarks. We also introduce a multilingual embedding model and a lightweight rear anchor that aids in training embedding models through distillation. In summary, our key contributions include the development of bge-en-icl, which enhances query embeddings by integrating few-shot examples, and our exploration of effective ways to utilize LLMs as embedding models. We emphasize that simplicity is key. Combining ICL capabilities with embedding models can lead to excellent performance. We provide open access to our model checkpoint, dataset, and training scripts for further research. In the related work section, we discuss the significance of text embedding in information retrieval, highlighting its applications in web search, question answering, and dialogue systems. We explain that effective retrieval relies on encoding queries and documents into the same latent space and calculating similarity scores between them. Recent studies have shown that pre-trained language models like BERT and T5 outperform traditional methods in embedding tasks. We also review various approaches that have utilized LLMs as backbone encoders for text embedding, noting advancements such as fine-tuning Llama 2 for dense retrieval and introducing pre-training tasks to improve performance. Other models have innovated by replacing conventional pooling methods and integrating text embedding with generation. However, we observe that much of the existing research has focused on altering model architectures rather than leveraging the inherent capabilities of LLMs. By utilizing the ICL capabilities of LLMs, we can create embedding models that are more versatile and adaptable to different scenarios without requiring extensive fine-tuning. Our model not only achieves state-of-the-art results but also effectively harnesses the strengths of LLMs across various tasks. Section Summary. In this section, we discuss the significance of text embeddings in natural language processing and highlight our approach of leveraging in-context learning, ICL, capabilities of large language models, LLMs, to enhance query embeddings. We demonstrate that by incorporating few-shot examples directly into prompts, our model, bge-en-icl, achieves state-of-the-art performance on key benchmarks without the need for complex architectural modifications. Section: Methodology. In this section, we discuss our methodology for improving embedding models through in-context learning, ICL. Traditional embedding models typically input queries directly to generate target embeddings, but this approach struggles with tasks that have different intents, limiting adaptability and generalization. To overcome this, researchers have added task instructions to queries, allowing a single model to adapt across various tasks. However, studies show that embedding models still struggle with unseen instructions and complex retrieval tasks due to a lack of diverse training examples. Inspired by how large language models, LLMs, generalize through ICL, we investigate whether embedding models can also benefit from this approach. We demonstrate that embedding models can improve their versatility across different tasks by using few-shot contrastive training. For each embedding task, we create a template that includes a task definition, which we apply to new queries. We then modify relevant query passage pairs to generate new queries, encoding all modified queries and passages using the same LLM to obtain their embeddings. We utilize a standard info-NCE loss function for training, which incorporates both in-batch and hard negatives. Our scoring function measures the similarity between queries and passages, using a temperature-scaled cosine similarity with a fixed temperature of 0.02 during training. Regarding representation methods, we note that LLMs typically use unidirectional attention, which may limit their representation learning. Research suggests that bidirectional attention can better integrate contextual information. Some models have introduced bidirectional attention during training, but we argue that this could conflict with the model's pre-training design. Therefore, we maintain the unidirectional attention mechanism, using the output embedding of the EOS token as the representation for queries and passages, aligning with the foundational pre-training of LLMs. For ICL-based instruction tuning, we recognize that while previous methods have used many task-specific instructions during training, this does not fit well with ICL strategies. Directly providing few-shot examples can degrade performance. To incorporate ICL, we modify the instruction tuning approach by integrating ICL capabilities during training. We provide task-relevant examples to queries, allowing the model to develop ICL skills. To avoid compromising zero-shot capabilities, we implement a dynamic training process where the number of few-shot examples varies from 0 to a set number, determined by a sampling function. This balances the development of ICL abilities with maintaining zero-shot performance. Additionally, we enhance ICL capabilities by using in-batch pairs as few-shot examples, helping the model better differentiate between examples and inputs for more reliable embeddings. Section Summary. In this section, we explore enhancing embedding models through in-context learning, ICL, to improve their adaptability across diverse tasks by appending task instructions to queries. We propose a dynamic training process that balances the integration of few-shot examples with maintaining zero-shot performance, while retaining unidirectional attention to align with the model's pre-training design. Section: Experimentins. In this section, we explore the effectiveness of the ICL training pipeline and reassess the training methods for LLM-based embedding models. We pose several research questions. 1. How effective is the ICL training strategy in zero-shot and few-shot learning scenarios? 2. How does ICL compare to traditional training methods in terms of performance? 3. What effect does including in-batch examples have on the ICL training strategy's performance? 4. What are the consequences of using a bidirectional attention mask instead of a causal attention mask in LLMs? 5. How do different representation strategies, like last token pooling and mean pooling, influence model performance? 6. Do passage-based prompts improve performance in the ICL training strategy? For our setup, we use Mistral 7B as the backbone of our framework, following the approaches of E5 Mistral, SFR, and NV Embedder. We evaluate our model's performance using MTEB, a benchmark for text embedding models, and AIR-Bench, which assesses retrieval performance with data generated by large language models. To ensure a fair comparison, we utilize the same public datasets from E5 Mistral, including ELI5, Hotpot QA, Fever, and others. While some methods like NV Embedder and SFR perform well, they often require more training data, and some, like GTE Quen 2, do not disclose their training data sources. To address this, we created an enhanced version of our model with a broader dataset that includes various training sets for retrieval, re-ranking, classification, and clustering. For training, we fine-tune the Mistral 7B model using a contrastive loss over a single epoch. We apply low-rank adaptation with specific settings for efficient fine-tuning. In retrieval tasks, we incorporate in-batch negatives, using a batch size of 512 for retrieval and 256 for other tasks. We maintain consistency by using the same dataset throughout training, with a maximum sequence length of 512 tokens. For in-context learning, we randomly sample between 0 to 5 examples from the training data for each query, with specific length limits for queries and documents. We evaluate our model under both zero-shot and few-shot conditions, using consistent in-context examples for the few-shot scenario. If training datasets are unavailable, we generate examples using ChatGPT. In our main results, we present the performance of our model, bge-en-icl, on the MTEB benchmark. When using the full dataset, our model shows strong capabilities in both zero-shot and few-shot settings, achieving state-of-the-art results in few-shot scenarios. However, using full datasets can lead to inconsistencies due to varying datasets across models. For a fairer comparison, we also evaluate using only the public dataset, where our model's zero-shot performance is comparable to others like LLM2-vec, but it shows significant improvements in few-shot settings, especially in classification and clustering tasks not included in the training data. In the AIR-Bench evaluation, our model outperforms previous models in both zero-shot and few-shot scenarios, particularly excelling in QA and long document tasks, with no overlap between training and evaluation data. The few-shot setting shows notable improvements over zero-shot, indicating the effectiveness of in-context learning. Interestingly, when trained solely on public data, our model performs better than when using the full dataset, likely due to the risk of overfitting from excessive MTEB-related data in the full dataset. Section Summary. In this section, we evaluate the effectiveness of the ICL training pipeline for LLM-based embedding models, addressing various research questions regarding its performance in zero-shot and few-shot learning, the impact of in-batch examples, and the implications of different attention masks and representation strategies. Our findings indicate that while our model excels in few-shot scenarios using comprehensive datasets, it may experience overfitting when trained on overly extensive data, highlighting the importance of dataset selection for optimal generalization. Section: In-Context Learning. In this section, we evaluate the impact of the in-context learning (ICL) strategy through a series of ablation studies using the MTEB benchmark. We compare the performance of models fine-tuned with ICL against those without it. For ICL training, we use two approaches: fixed examples and in-batch examples. In the fixed examples approach, each task is trained with 3 set examples. Our results show that when the model is trained without ICL, it achieves an average performance of 64.83, similar to models like grit-LM and LLM2-vec. However, using fixed examples during ICL training leads to a notable drop in zero-shot evaluation performance by 3.33 points, likely due to the model's repeated exposure to specific examples, which hinders its zero-shot abilities. Conversely, in few-shot scenarios, the model performs better, exceeding zero-shot results by 3.96 points and outperforming models trained without ICL by 0.63 points, confirming the ICL strategy's effectiveness. When we use in-batch examples, which may involve 0 examples, the model maintains its zero-shot capability with only a slight decrease of 0.16 points compared to the non-ICL model. In few-shot scenarios, the performance rises to 66.08, showing a robust improvement of 1.25 points. Additionally, the model using in-batch examples performs better in tasks that differ significantly from the training data, such as classification and clustering. We also explore the effects of modifying causal attention in large language models, LLMs, to include bidirectional attention and mean pooling for embedding generation. Models like grit-LM, NV-embed, and LLM2-VEC have successfully used these techniques. We investigate the benefits of bidirectional attention in the ICL context, examining various attention and pooling mechanisms. In a causal attention framework, each token can only access information from preceding tokens, which limits the effectiveness of mean pooling. We find that the model struggles to train effectively under ICL, so we only present results from experiments without ICL in this setup. Our findings indicate that in non-ICL scenarios, most methods perform consistently, except for the combination of causal attention with mean pooling. In ICL scenarios, the best results come from using causal attention with last token pooling, aligning well with the model's initial training. Switching to bidirectional attention does not yield significant improvements, and mean pooling is unnecessary for it. However, configurations with bidirectional attention and last token pooling perform well in both non-ICL and zero-shot scenarios, showing strong results in few-shot re-ranking tasks. Lastly, we address the limited research on using prompts on the passage side, as most LLM-based embedding models focus on instruction-based prompts for queries. We introduce prompts for the passage side and present our findings. The results indicate that using passage prompts leads to a significant drop in performance across all tasks except retrieval, suggesting that more exploration is needed in this area.